Professor Jayant Narlikar. We are gathered here today to celebrate a towering figure in Indian science, a visionary cosmologist, institution builder, and a passionate science communicator. In this regard, I request our director, Dr. Guru Prasad sir, to escort today's speaker to the dais. And I request our director to formally welcome you all and introduce today's speaker.
Professor Tarun sir, academicians of the dais, invitees, friends from the media, students, ladies and gentlemen, good afternoon to all of you. I am indeed honored to welcome Professor Tarun Souradeep and along with him, all of you, I welcome to this program and legacy of Professor Jayant Narlikar. And I need not say who he was, all these things. It will be a cliche. And I have one more pleasant task to perform, which I will do with pleasure, apart from welcoming. That task is none other than introducing Professor Tarun Souradeep. Professor Tarun Souradeep, a distinguished cosmologist himself, is the present director of Raman Research Institute, Bengaluru. Professor Souradeep graduated as an engineer from IIT. Interesting, isn't it? After a short stint in automobile design, he decided to pursue a PhD in gravitation and cosmology from Ayuka, Pune, where he worked under the supervision of Professor Jayant Narlikar for the first couple of years. Professor Souradeep carried out his postdoctoral research at the Canadian Institute of Theoretical Astrophysics and at Kansas State University before returning to a faculty position at IUCAA. He is currently on deputation leave as a distinguished professor at IUCAA and has also been the chair of physics at IISc. For about 25 years, he has built and led a cosmology group on cosmic microwave background CMB studies. Professor Souradeep also led the sole Indian group within the international team of the planned CMB space mission of the European Space Agency. Co-recipient of the Special Breakthrough Prize in Fundamental Physics in 2016, Grover Cosmology Prize in 2016 for the recent discovery of gravitational waves. Exciting. He is also a recipient of many awards in India, including Swarna Jayanti Fellowship, NASI Scopus Award, B.M. Birla Prize, Vikram Sarabhai Research Award, Shastra Award, amongst others. Professor Souradeep is a fellow of the Indian Academy of Sciences and National Academy of Sciences of India. Professor Souradeep served on numerous key roles in the LIGO India Mega Science Project till 2023 and currently leads an ambitious space mission proposal, CMB Bharat, to ISRO, targeting the discovery of primordial gravitational waves emanating from the birth of cosmos. I am extremely happy, naturally, that a person of Professor Tarun Souradeep's eminence has graced this occasion today as the speaker. I welcome him once again. Sir, now I request you to deliver the talk. And before that, just I would like to announce this is the first lecture program in C.V. Vishweshwara Auditorium. And none other than Professor Tarun Souradeep is delivering the talk here. We are extremely happy to have Sir, the stage is yours. Thank you.
Yes. This is quite a opportunity for me to be able to pay respects to two great people who have influenced my early days of research at one go. I mean, Professor Jayant, of course, you mentioned. I joined IUCA, and in the initial years, I was essentially working under him. Although he really did not, he allowed me to do whatever I wanted. I mean, it was an amazing time to be working with him. And also, I'm glad that I'm the first speaker of the CVV Vishweshwara Auditorium, because Professor Vishweshwara is probably primarily responsible for me moving from engineering to physics. I mean, if I want to at least find one reason, that was because he gave some 13 lectures in GR, which I didn't understand much during my undergraduate time, but it was fascinating. So I sort of decided I would do work in GR, and I had that opportunity, but I had to choose between the two of them. And so let me now talk about Professor Narlikar, and also this talk is, I was a bit confused about which way to pitch it, because of course there are a lot of young people here. So there's of course a lot to talk about him. His personality is so broad and touches so many aspects that you can almost give a talk on any one of them. And I chose to emphasize how he felt about science as I understood it. So I'm not a science historian. I haven't really dug in to really verify every hypothesis I made. But this is like I've been with him for many, many years. And this is what he felt about science. And I will try to express that. So, of course, this is a very telling cartoon which came out, and I thought I'd start with that. So, this sort of tells you why common people across Maharashtra or across India, in fact, thought so much of Jayant. Jayant was really, if there was, Bollywood star among scientists in India, I think it was it. Right? I mean, I have met so many people, including very senior people. I think Professor Rajaram told me as a young person, they crowded in to hear him talk in 1965 and things like that. So he was like a huge figure, and he maintained this connection to the masses. That I felt is a amazing commitment. That not only he believed in scientific excellence, which at IUCA was very clear. I mean, he had a scientific advisory committee from all over the world, always watching what we are doing. But we were all told to then take it and spread it to the university and also to the people. I mean, I remember from my graduate student days that, we used to take summer students. Every graduate student used to take summer school students. And towards the end of my PhD, I sort of tried to excuse myself from it. And he didn't say no, but he told me that you should remember, Tarun, this is part of your job. You should look at it like an extra work that you're doing, the part that you're talking to students about. I think that stayed with me. I've been always very happy to talk to students. But this part is amazing because when I came to Pune, I mean, I have never felt one personality being known so well, and someone from science being known so well amongst the people. And so I will be sort of giving a very personal reading of his legacy. I mean, as I said, this is not from a science historian. But let me just start with some pictures so that you're familiar with him. So this is Jayant, Professor Jayant as a kid, like any of you, or maybe even younger than any of you. So, but he was very bright. He used to be very studious, that is known. And his parents, actually at a distance, but his parents, he was blessed to have parents who were extremely eminent. So his father, Professor B.D. Narlikar, was a giant scientist. He was a relativist of India, very well-known relativist. His mother was very well read in Sanskrit, and he had this academic environment. He was brought up in PhD. And then, nevertheless, his own brightness, he ended up in Cambridge. This is a photo with many people, including Stephen Hawking. I won't really go into that much. And then this is something very interesting where he is holding discussions with Fred Hoyle. Okay, someone who really inspired his entire thinking in science, right? And this is quite a unique set of pictures. And then he got his PhD from there. But around that time, he did a work where he proposed a complete alternate view of the universe, right? I mean, it's not that it was originally already being talked about, that there would be steady state option to Big Bang, and Big Bang itself was not very well established at that time. You should see this as a typical thing that happens in science. There are two ideas, both at that time pretty viable, and then of course over time observations come in and start deciding which way to go. And when he finished his PhD, he was also extremely well known in India, because I think what really attracted Indian masses, this is again my interpretation and I'm happy to be corrected, is this fact that the universe that he was proposing had more to do with how we think philosophically in India. We have this idea that there's an eternity, and we were very comfortable with the eternal universe and the fact that some things don't change and unchanging on the average. And so he became a star. So this is a picture which is from what is called the Bharat Yatra, and this is probably 60s, 65 or maybe. And he went to almost every town that I have heard about, well-known places, gave lectures, which I am told people just crowds came for those lectures, right? I mean, it was not just a lecture. So somehow they shot into fame, and then was invited by the president to come back to India. He joined TIFR, and of course he got married to Mangala Narlikar, who herself was an academician and steady partner to him all through his life. But that part I won't really dwell on. He got the Padma Vibhushan. Before that, right in the 60s itself, when he came back, I think he got the Padma Bhushan. So let me talk about the universe. So I titled it as Our Universe and Our University. So these both two things are close to what Jayant was very interested in. I was wondering if the lights can be reduced here, because this light is on somewhere. You would see the Milky Way. Actually, I saw it pretty late in my life because I was brought up in Delhi, and I happened to be on a bus which broke down on the way to Manali, and we were in pitch darkness, and I was asking my brother, what's that on the sky? So this is the Milky Way, and if you look at it, these are stars. We realized not too long ago, about 100 years back, we realized that the universe is more than these stars. We are not an island universe made up only of these stars around us. But if you were to peer away from the dark region where there are no real stars, there are other island universes. And of course, over time, for example, we have looked at it with deeper and deeper, deeper with more and more capable telescopes. So if you zoom on in this tiny patch of the sky, you would see something like this. This is what James Webb Space Telescope sees. It's sitting very close to Earth. On cosmic scale, it's sitting near Earth at second Lagrange point. And then the universe is full of galaxies. Okay, galaxies stretching back in time to such an extent that some of them, we are seeing them as they're just forming. We are almost seeing the first galaxies form. And this is all there. There are maybe more than 10,000, I don't know much better, but maybe a few 10,000s of galaxies in this brain. We are seeing some of them. So what is interesting is, we know that the universe is enormous, it has a lot of structure, it is vast. Right? So if you are doing science, you try to then understand how do I get hold of it? How do I model a system? Right? So you have to find some way to make it practical. And you do that in your problems. Many of you are school students, so maybe you are not got to that. But often you say, okay, let's forget about this part of it and then try to abstract out what is essential. And so what was essential when Einstein had general relativity, he said, okay, let me assume that the universe has a homogeneous distribution of matter. Everywhere the isotropic and homogeneous distribution of matter. And then use my new theory of gravitation. So, we are in an amazing era. It was again just about a century and a couple of tens of years, maybe 120 years, 110 years that we understood what the theory of gravitation was. If you applied it on the cosmic scales, which I should mention is also a very unique thing, Newton's theory cannot be applied reliably on cosmological scales. Newton himself tried and knew that that was a problem there. But when Einstein did it, it naturally led to a expanding universe. It could expand or contract, but there was, it was not normal to have something that was static. Now, imagine that scientific discovery is quite mind-boggling for a human being. We believe everyone, few centuries back we thought the sky was static, right? Nothing changes as shifts here. And now you're telling me that the whole universe is evolving in time. But that is what we have now. Okay, and this was verified by Hubble. And so there is a consequence of that. So I am now telling you what we believe is the standard cosmology. So if you really look at a box of, hypothetical box you draw in the universe, and you count up the galaxies there. Okay, the universe is expanding, so there was a time when everything was half the distance away from each other. Okay, then you will see that the number density goes up by, factor of 8, plus 2 cubed, and then if it's 1/4, then it's 4 cubed, and so on. And the energy density, using Einstein's, mc square, mass c square, will also grow like that. But radiation in this box would behave very differently. The number of photons, the number of particles of light would be doing the same thing as galaxies. But each particle, given that their size is shrinking, the wavelength is shrinking, will gain another factor of 2. So energy density, instead of being factor of 8, will be 16 here, So this rapidly grows, and you see that the early universe would be completely radiation dominated. Okay? So radiation dominated early universe, highly dense radiation, will have a temperature if it is normalized. And that's why you have this idea of a hot early universe. And that's the current the favored cosmology of hot Big Bang. Right? So, and if you take this expansion and mathematically extrapolate it to the beginning in a finite time back in some finite time, maybe 13.6 billion years ago, the universe would have been infinitely dense and but that's the extrapolation. And this whole picture, became really set, as I said, when there were two models. There was nothing which differentiated one from the other. We didn't have enough observation. One observation that played a big role in this is the serendipitous discovery of this radiation. We said the early universe is radiation dominated, but where is that radiation? And we discovered it, and it's called the cosmic microwave background. But this happened in 65, and by the time the whole thing got settled, there were other options. And if you look at that, then essentially a way to think about it is we are sitting here, and in any direction you look in the sky, we will eventually hit a plasma screen. Okay, so this is like an IMAX theater, and literally we have an IMAX theater with the screen placed 43 billion light years away. Okay, and we can, in the hot Big Bang, see a universe which was about 1,000 times hotter. So, and this temperature is about 3 degrees Kelvin. So this is about 3,300 Kelvin or centigrade, at that level it doesn't matter. And then at that time, anything in the universe will be ionized. This is basic physics, right? And hence, this allows us to use basic physics to understand what must have happened there. We also believe, we know how structures like the galaxies are not formed. We see tiny fluctuations in the temperature on this, and they grow and give you this beautiful distribution of galaxies that we started off with. Okay, so it's all clumpy, beautiful thing, but you can explain, there's a consistent explanation. But in this thing, we always hide something, okay? So to make this story consistent, we have to also explain what gave rise to this perturbation. But so as we are going back in time, we are going to higher temperatures, so we are hitting scales of physics which we have not accessed. We don't have clear theories. So we hope something will come up and explain. And we have good hypotheses. I'm not saying we are, absolutely blind, but there's nothing which is observationally verified or experimentally explained. Okay? And that has really gone forward with, if you don't worry about this part, then given this and this, you have very good measurements of the cosmological background over 3 decades. And that allows you, in that particular model, to know what the values of various things are. How much of ordinary matter is there in the universe? How much of, cold dark matter and things like that. Right? How old is the universe, for example? So it's amazing that you will see that the age of the universe here is kind of known to this kind of accuracy. Now, this is assuming that particular universe, we believe that age will be that. I mean, it's strange that human beings sitting here in this speck of dust, we can confidently say the universe must have been that much old. Okay, so there is a particular model that works. Okay, now I wanted to quote Jim because most of us are really very excited when the Nobel Prize winner says something. So I thought, whatever we are going to say later, I wanted to say. I was very uneasy that people are accepting lambda CDM so readily. And I spent much of my time inventing viable theories. I was started by 1990s at where lambda CDM was working, and I'm still starting. So imagine that the person who had one of the greatest credit and was created with Nobel Prize to do that, still is uneasy about it because you are talking with the cosmos, right? And you want to be very sure that you have thought it through. It has not only there's not only physics, but there is also a bit of philosophy involved, and there is also a bit of humility that we should have. So what is the current universe like, and why he says surprise? Because most of it we don't know. Of this matter content of the universe, so it's a pie chart. I mean, it's like a cake. So of the cake, we know only 5%. It's like, you have a cake and you get to eat only the 5%. The other 5, you actually don't see. But someone tells you, you have a full cake there. Okay, so there's 25% dark matter, 70% dark energy. And even this part, is broken down. We know what are the fractions. So I just wanted to tell you, the stars of it make 7% of this 5%. And I'm sure all of you will be able to tell me what that percentage is. Okay. So let's see. So while we have very happy in cosmology that we have a working model, and a lot of people have started calling it the standard model, we should realize that it is built on simple principles. We kept things simple, but yet it's exotic enough that it should worry us. So 95% of the energy density, we have no idea what it is in terms of, we have guesses, but no experimental evidence or observational, verification of what that is. We can't see it directly, we only know because gravitationally we see its effect to some extent, and the cosmology works if you invoke it, only if you invoke it. And then, as if this wasn't bad enough, we also have another form of energy which we are not even it's different content. I mean, we believe any matter, gravitation, all of you know is an attractive thing. So any matter from clump would always collapse. But we believe most of the energy density in the universe is such that it doesn't cluster under gravity. Okay, and we call it dark energy. And these are dark, anything in cosmology means we know nothing about it. Okay, and I didn't put the quote from Stevens, but this is really after his Nobel Prize, he said, yes, everyone is free to ask me what is the cold dark matter, and I have to say, that we don't know. Right? So these two are there. I actually also think that this is an immense problem. We have pushed all our things to the early moments of the universe whose physics we don't know. We believe there is some ultra-high energy physics, possibly fundamental, which generated the perturbations, because without that there is no consistent picture. Okay? So this is the current cosmology starting from 60s to now. It's working. I'm not saying cosmologists are not doing it right. I mean, we are doing honest science. There is no question about that. But if you step back, you need to think about. So in this context, let me again give these two quotes. So he says, I think I'd be depressed if everything were nearly all known, but I don't feel any danger of that happening. Okay, these are recent quotes of a cosmologist. Okay. And he's been there from the 60s. He's a contemporary of Jayant, and I also point out that I have had discussions with him about Jayant Narlikar's views and things like that. So, and then he also has this quote which is very interesting because it has some bearing on the pursuit that Professor Narlikar had. Since it's always a good thing, and there is a chance nature has prepared yet another surprise for us. Okay, so this again tells you that a lot of people naturally, all the time tell you think out of the box. So we should always think out of the box, but we should know what is the value of not necessarily following a set pattern. If something occurs to you which seems a bit deviant, you should pursue it. So let me now talk about Professor Narlikar's point of view. What did he feel about cosmology? And again, there is no single article where he says it this way or that way. So I pieced it together from various books and some of them. So this is a book that Jayant Narlikar wrote with Geoffrey Burbidge. It's basically almost like a compilation of a lot of work that they had done over time. And I should tell you that how much of it is really are facts and how much of it he calls it speculation. But I would also say they are more theoretically motivated ideas and yet to be experimentally verified. So as I said, our standard picture is there's something that happens, Big Bang, because it's an extrapolated thing, all the energy densities go to infinity, we have no physics that it can explain such things. And then there is light, yes. So we all club it saying some quantum gravity, when it comes, will explain it or some other view. Then where did all the matter come from? Okay, all the matter has to be created, right? Okay, and we believe that we know there are processes which we can kind of write, equations for, which may be able to create all the matter, and this is grand unified theory and inflation. This is supposed to have happened at 10 to the minus 37 seconds. Okay, but as I told you, all this are things that what do we know for sure? Okay, we know for sure this part of the universe. We know for sure that this one is a bit iffy, but up from here to here is absolutely lab physics. This is also lab physics, this is nuclear science, and if you really want to say where are our experimental capabilities, so as I said, as you go back in time for the present era, you can talk about the energy density of the radiation, so a temperature to the radiation or energy. So this is like 10 to the minus 1 millivolts. electron volts. But don't go by this, even if you don't know what electron volt is, just compare the numbers. So it's 1/10 of a milli electron volt. Milli means 10, a million times smaller than this number. And then this 1 milli electron volt, where all the structures form 100 milli electron volts, where we see the cosmic microwave background. And then if you believe elements were cooked in the universe, then it's 1 million electron volts. So up to that, of course, there are labs where you can check out the physics, and we know the physics very well. In fact, we know the physics probably quite well experimentally up to this limit. Who knows what LHC is? Large Hadron Collider. It's the most energetic accelerator facility we have, and it goes to about tens of tera electron volts, so that's about 10 to minus 2 giga electron volts. But you see, this is the part that we can say, okay, there's a robust picture consistent with. All this is theoretical expectations. We have well-motivated theoretical models, theoretical theories, but we don't have any way of being sure which one or what physics is working with. And this, I believe, was the point that Professor Narlikar always used to, so if you don't mind, I keep calling him Jayant because that's what I call. So Jayant used to always point out, you can just over coffee and all that. So, we building a lot of things here, but we need to really focus on finding ways to verify what we do. And the danger with this game is we have pushed things to such high energies that in the conceivable future we have no way to build a lab where such energies will be realized. Because the universe itself becomes the laboratory where you can check anything here. So this LHC can go up maybe by another factor of 10 or 100. Beyond that, it's impossible. So then, this part, what we think is standard cosmology, there's a huge onus on us to make sure that we believe it's not speculation. So what I'm saying is, if they wrote it very provocatively as facts and speculation, as an honest cosmologist of the day, I can't say, oh, no, they are not speculations. If you want to call them speculation, fine. If you want to be a bit kinder, you can call them theoretical, expectations. And, sorry, this didn't come, but this was essentially the same, this is the caption of this figure from this book, which essentially said what I said now. Okay. Now let me talk about the steady state universe for which he is very well known. So the steady state picture, so here is our universe. In those days we used to believe that's expanding and then the expansion rate is slowing down and this is what will happen. Steady state universe, the expansion is eternal, so this curve goes to minus infinity. It's always expanding at a given rate, and this is what the curve is, steady state. The first hits came from the fact that this is here the rate of expansion is increasing with time. It's exponential curve. And people's first criticism came that no, but our universe is not expanding faster and faster, it's not accelerating in expansion. And that was the biggest, immediate hit. So, but this was an expectation, and at those times, there were various, observations which favored Big Bang versus steady state, and I will get into that. But I should tell you that currently the best model actually is also expanding exponentially at this time. Okay, this is something that people came to in '98. They came to agree about it. Okay, and so this is basically the viable, or was a viable alternate cosmology certainly in the 60s. Okay, and I'll tell you where the difference is here. So here the biggest difference is, Bondi, Gold and Fred Hoyle you know, they propose a steady state theory, creation of destruction of matter. And, oh sorry, this is, yeah. So there's no creation or destruction of matter, and all the creation of matter is at a time which we can't even access now. It's very early in the universe, some height. So this is why we are happy at this point. Steady state took this opportunity to say, okay, let's try to see if all the current physical laws can explain the universe we have. There, what would you need if the universe has to, expand yet remain the same for every galaxy? So it's like this box. If I did not have these red dots, the blue dots would have diluted, right? Number of blue dots per volume would have come down. So you create red dots, which are new matter being created. Okay, so what was Professor Narlikar's biggest thing? He came up with a mechanism where this can be enacted. So there was something which said, okay, that we can have creation of matter, but there is a how. And he used what was at those times fairly close to field theory. I mean, that was field theory, and again, that was very early days of field theory. But it was an observationally viable alternative plan. Okay, so this is from the picture from the book. Like these are galaxies. So these are, the whole thing is expanding out. So these galaxies would go outside the sphere, the ones with an arrow, and then new galaxies would be forming, and these would come out to the edge, and then new galaxies would be forming continuously. Okay, so this is how much I will talk about the cosmology part of it, steady state versus Big Bang. The point I wanted to make is, if you really look closely, there's one particular place where there's an assumption, right? That number of galaxies are being, so what your physical density of galaxies is conserved. Their number of galaxies per physical volume was conserved here. Physical density of galaxies is conserved. Okay, so but that requires a continuous creation of matter. So your current universe should also include a way of continuously creating matter. Okay, this is one way of thinking. Here, everything is in the universe that you see now, and you have to explain. The other part is we explain the part that we can see, and what we can't is all to be discussed. So these are two viable ways to go forward. And I should say the steady state in detail does not work in terms of observation, but that doesn't mean the basic idea that the universe, you should be able to explain the universe with everything at this time. Maybe a very nice way to think of it. Okay, now to just tell you what kind of mindset he had as a physicist. So Fred Hoyle and Narlikar worked on something which I think was rather, the name is what really attracted a lot of criticism. It says action at a distance. Now, in every of you, although you may not know the physics behind it, know that you cannot influence a body far away, faster than the speed of light. No information can travel faster than the speed of light. Right? So this is something that we have learned from special relativity. So if interactions are instantaneously propagated, then there's a problem. But interestingly, if you do field theory, okay, and you look at something called how does one particle, suppose some particle influences this guy. So you move this particle, sends some wave, and then this, right? So this is called a propagator. The effect is propagated along this. Right? In this, I'm looking at time this way and space this way. Right? So this is called a propagator. Mathematically, actually, there is also a propagator from here, which is going back in time. Mathematically, you cannot distinguish. There is no way to say this is better than the other. Yet, as physicists, we just decided to throw away this thing because it looks odd. I mean, how can something in the future influence me? Right? So that is how we think. But mathematically, there is no choice. But Feynman and Wheeler essentially he constructed a physically consistent model where both the possibilities are kept, yet you see what you see now, that there's no causality violation. And that requires the universe to play a big role. The universe is not just, arena where everything is playing out, but the universe is actually determining the laws of physics. And this is something that I believe, at least in the body of work that Narlikar did, was quite central. He always thought that the universe must have a bigger role, and that one of the roles could be that it determines the laws of physics. And this is one arena in which this happened. So Wheeler and Feynman had a way to keep both this so-called apparently non-physical propagation back in time, because mathematically it's allowed. Yet, the universe can have properties which allow you to have a consistent theory. So there are again nice books on this. So I should say that this is a book which I read through a bit of it, quite a bit of it, during my first year. Not because Narlikar Jayant asked me to do that. I was just curious. And it was really nice pleasure, and again thanks to Professor that I again, last week went through it to make sure I understood it right. And there are more accessible lectures I find that he has published. He has published a lot of books. So my table, I asked that nowadays assistant library to bring me all the books of them. I have quite a few of them, but they're scattered and I don't know where they are. And I was very impressed. There is another book in '86 which he wrote with one of his very illustrious students, Padmanabhan. And I wanted to point out this general feeling that Jayant Narlikar never accepted Big Bang and never worked on it. That's very far from it. Okay, so this book, for example, sketches out what happens now if you really want to summarize this. This is okay. You believe in Big Bang. Now, what should you be worried about? And he worries about exactly the same thing. He says, okay, Big Bang means you have general relativity, you have quantum field theory, you have all these quantum effect theories, everything. You have an early universe where something is supposed to happen. He also said, but this energy scales will also hit the point where gravitation has to be quantum. So you need to know quantum gravity. If not quantum gravity, then you at least should know how quantum gravity affects the cosmology and quantum cosmology. So with his student, he worked on quantum cosmology. Okay, again, this was some particular kind of quantum cosmology, and of course, Paddy went on to do a lot more on these things. But this is basically, so if you want Big Bang, then you have to accept that physics at all energy scales will play out, even the highest energies. Hence, you have to really have, you have to really worry about the fact that we don't know the physics at highest energies, and in particular, quantum gravity. These particle physicists somehow are very confident about these things, but, and hopefully someday they'll be winning. Gravity is something that relativists like us, we go to gravitation cosmology, we worry about how this could play a role, and that's something that we okay. So now I will just try to go over a few other aspects of it. So this is how much I wanted to do. I wanted to tell you two things. One is, I see here a person who thought very deeply. In India, he could afford to keep that thought and plow away on that. I think anywhere in the other country, particularly the US, you would not. I think that's a positive in India if used well. So let me now tell you some things that I should say. He is a great scientist, but his commitment to educating the next generation is unparalleled. I think amongst the teachers, he is the best, most meticulous. His lectures started at a time and exactly finished 45 minutes or whatever time he had, and he covered whatever he wanted. Very, very, very well prepared. And he has excellent textbooks, which I think are still very, good textbooks for cosmology. And it also tells you that it's not as if he didn't know what was happening in the other areas or what was the current cosmology. So totally impressed with it. So he was a very good teacher, very sincere. I mean, this is a picture from the time he used to use, I think, blackboard in Ayuka, which are now residences. So, other commitment was to students. I mean, I have never been able to keep up with that. I mean, he responded to every letter that came from him. I struggle to keep up with the emails, but I try my best. But you see that any student was accessible to him. He would sit and talk to them, give them time, and he always, you see this routine. There's no, he had time for that. I mean, he always had time for that. So this is here he is lecturing, to students. Remember that at that time he had the institute running and he's trying to do some other things too. But this is what he's doing. Here, I mean, with some school kids again, and with Mangala also used to compliment a lot. And then I would say the commitment to the next generation as well as enabling science to be accessible to masses, which we are actually getting the benefit of. I mean, the fact that I can go to Pune and go to any part of Pune and ask the rickshaw driver, I want to go to Ayuka. You won't even ask which Ayuka, where, what. I can guarantee you the driver is going to bring you to Ayuka in Pune University. This thing is remarkable. Again, as kids you may not realize it, but someone who made science completely something that people felt ownership of. They felt that they had a say in science, or they had to support science. And we make the best of it. This is just a selection. I just didn't get time to put the rest of the pictures of the book. I have them on my drive, but these are lots and lots of books. He wrote some fantastic popular science books. I mean, this is like semi-popular, trying to, the rest, I would say books are like that, and very few which are that well written. His popular articles were very, again, interesting. And secondly, I would say his science fiction was some amazing thing. Like, I can give you one example of science fiction. So there is someone who discovers a statue of Ganesha, okay, and this sharp guy, he notices that the trunk is actually going the other way. It goes to the left, the Ganesha's trunk is turned to the right. Okay, now this could be some artisan making mistake, but it could be also that this Ganesha has traveled around the universe, and the universe has what is called a twisted topology. It's like a Klein bottle, where a left-hand glove goes across and comes back. This is a very esoteric possibility, but you see how much importance it gave to the universe. But we don't know if the universe is doing that, because we don't know many things. We don't know why antiparticle matter is not seen as much as matter. A lot of questions. And these exotic possibilities are not even things that we are looking at, but he brought them to kids. I mean, at least you realize, oh my God, this can happen. Right? So there are things of that kind. And I also would say that I have never seen anyone so committed. Anything he said, oh, I support. I think it's a good idea. I mean, it's unbelievable. We were doing LIGO India, and Bala is here. So, and I was very, very touched when in 2017, when we had said, I told him that we have a site, we know which site we are going to. He said, I want to go and visit the site. At his age, this is not easy. Right? It's a remote site. It's not very pleasant to just travel so much. He went there, spent time. I am not in this picture. The only reason you would know I was there is because this cap is mine. So I gave him my cap because it was so hot and he refuses any help. That was another problem. It's a place where people faint and all that. And then we had this science exhibition traveling 4 cities. And Jayant made it a point to come and, spend time at the exhibition as well as with the library team. Okay, he was not really at that time the director of the institute or anything like that. I mean, in fact, he's probably the only director or definitely the first director of any institute to have visited society. Till then, all of us who were at the workers used to go there. So this commitment is unparalleled. I have not seen anyone, maybe Souradeep to some extent, but I think this is something that you should learn. I mean, if you believe in something, you have to put your whole heart and, and it's not just saying, oh, I'm going to attend this or something. You have to show that, you have to do the right things. And that, I think, was amazing. The other thing is this commitment to scientific temper. Right? We all say we have to have a scientific temper. We also worry that often things are said which are not scientific. Okay? Many of us open pages of newspaper and find unscientific. He was against it. We are all against it. Many of us are against it. I'm not saying we all, I don't believe every scientist is, but many scientists are. But we don't take that trouble. He has been vocally against it. He would just rise up and do that. He did experiments to try and prove them wrong. So, and these are his quotes, And he believed that the job was ours. He didn't say, oh, those guys like that, and so you can't do anything about it. That's not true. He said, if your job is to replace, whatever is fallacious in their understanding with the real knowledge. So that is our job, not, and that I think is another thing I heard. He never was, he would never say, oh, this system doesn't work, that is. It's not just, it's up to you. You have to try your best to work it out. And these are some statements which he made about this part is what I think is the most important for us. I mean, if we believe that these have to go, you can't expect the change to happen on that side. You have to enable the change. Right? And that is something that I heard. Okay. The other thing is commitment to Indian universities. And this I found in an interview, but I knew this. Essentially, the question that is often asked is why hasn't India got Nobel prizes? Why hasn't, Raman was someone who got it, but after that no one. They're very good theoretical physicists who have done great work. What happened? One of the problems which he said is the main reason for this is that we had allowed our universities to run down. Okay, so the university sector, actually, I don't know, but post independence in the first 50 years was actually very strong, but apparently isn't. And he wanted to do something about it. Right? So the momentum that universities had gained during the initial days of independence has dissipated. Then how do you expect that system to work and produce it? And he strongly believed it can't happen in ivory towers of excellence in few places. So that was, I think. So actually, again, he believed that, but he did something to, at least, help with that situation. In astronomy and astrophysics, this Individual Center of Astronomy and Astrophysics was set up. I think this is going to be the biggest visible legacy that Jayant has left. It's an amazingly set up institute. This is, of course, the architecture is fantastic. It's Charles Korea, so it's a lovely campus. If you get to go to Pune, you should go and visit it. And you see, all the things that were dear to his heart were actually in the 8 directions in which the teaching, interactions with projects, bringing observers, basic research, advanced research, visitors from the university course, and then there was public outreach. Okay. So this is his goal. This is what he wanted to do. This is from a blog that he was keeping in the recent years. They are very beautiful articles there. I encourage you to read them. Just look up Jayant Narlikar blog and you find them. You can subscribe to it, and it's lovely. So this is from that. So apart from being a center of excellence in basic research, to help academics from universities upgrade their work. What he envisaged is Ayuka by itself will be a center of excellence. He absolutely was quite strong about it, and it didn't mean that center of excellence is his idea of the universe only. The first cosmologists he hired were actually totally, from schools of Big Bang, to top schools of Big Bang. So it's nothing of that kind. But the whole idea was they were supposed to go out and spread the knowledge. To some extent, Ayuka has been successful. The authors argue should have done much more, and that time will tell. But this remains, I think, the biggest challenge. If we want to do something in memory of person Narlikar, then to me, if we can create this system where the institutes that we have built up, which are good, have a mandate to actually reach out and try to pull up research in the university sector. And some of you are doing that, so would know what it means to them. So this is Ayuka. This is the early days. I was there. I joined when Ayuka was just one building, and the rest of it just had boards saying something will come up. Ayuka West being. But soon it came up, and we attracted the best in the university. This is the foundation stone of Ayuka. You see the same frame, Chandrasekhar, Govind Swarup. I think this is Rad, but I'm not completely sure. And many others here. I am hiding here. This is Chandrasekhar again, Rashtekar, Ithorn, Fred Hoy, and I could have made many slides of these things. Essentially, he had a center of excellence to be the global excellence people came. We had scientists who tried to be at par with the global standards. And also, it was not just a very focused institute only doing science, nothing else. We did public outreach, but he had this other part. He was a writer, right? So here's a picture with Pura Deshpande. I mean, they were so close that Pura Deshpande actually endowed some of his money when he passed away. He had money to set up the science communication center. So we had, a lot of meetings. So this was downloaded before I added the other few pictures of other slides. But similar meetings happened internationally and many places. So I always wanted to end with this thought that if this occasion again came, this is where we had a new fancy cappuccino machine. Jayant actually was you. But when I told him we have set up this cappuccino machine, he said, okay, I will come and try it. So we are having this coffee, and so if I were to talk about what should I be doing as a cosmologist, I think you would correct me, because I used to give talks to students saying the universe unraveled. Okay, because of the cosmological background, it's yet to be unraveled. And I'll tell you why. Because we have a very simple picture which seems to work very well up to a particular time. Beyond that, it's a mess. And in fact, this picture I drew for his 80th birthday fetch him, and this thing was called Probing Beyond the Cosmic Horizon. The idea is we don't know what we may discover, what new things we discover, because the universe is not a simple thing. I mean, you can't just say, okay, we have done it, and up to this point, and we have this. It will go on. Thank you. We know it exists in the sense that we know that there is matter that clusters under gravity, but it doesn't interact with light, so we don't have any way of seeing it other than the fact that its gravitational effect is consistent with its presence. But it's dark. Sorry.
What does the Hubble telescope see?
What does the Hubble telescope see? Hubble telescope sees galaxies very far away. It's a 2-meter telescope, but it is in space. We have 10-meter telescopes and 30 meters coming up soon. But we have, on Earth, there's a big problem because atmospheric turbulence doesn't allow us to see very well. Hubble Space Telescope in space, so it can, even with a 2-meter telescope, see extremely well things that we can't see from the ground. So it sees very distant galaxies. It sees, in the cosmological context, can see very distant galaxies. And it also works in a waveband which is not as accessible from the ground, so it is, it has things that you can see from optical, but also other capabilities. The third thing I should say is it's not only looking at faraway galaxies, it also looks at Jupiter, it also hunts for unknown planets or...
Before the Big Bang theory.
So that's the big thing, right? So we don't know, so we don't even know how to think of the Big Bang, right? So mathematically, if you just believed in GR, general relativity, that is the theory of gravitation, we should end up in a crunch. I mean, there's a singularity, and it's a prediction, which is why Penrose got the Nobel Prize. They said in this particular setting of cosmology, you have to have a field associated with it. What is possible? What does the mind allow you to think of? So are we limited by those rather than, so maybe 300, I mean, we laugh at, the cosmology of the Aztecs and all that, but maybe, 1,000 years later, people will say, these guys thought the universe was like this. It's very possible. So we don't know what, we know the Big Bang, but maybe there's no Big Bang or there is something that someone will discover. It's open, very openly here. And that is at an ever-increasing speed, and we are seeing some distant galaxies. Those will slowly fade away from view. We will only see galaxies in the future which are gravitationally bound to us. So we may still see Andromeda and some of the galaxies close by, maybe some of those cluster, because they're falling into it. But it's a very bleak, cold universe. Specific cyclism, he has certain predictions for the cosmological background. I happen to work in that area, I'm probably one of the experts in this area. Those are not there in the data. Okay. So some people think there is something in the data that's not there. One of the students looked at it very carefully. On the other hand, again, this is a question of philosophy. I mean, it's like the universe getting reborn and coming again. The cyclic expansions. It may be possible, but then you have to be consistent with the universe that we see now.
So is there any proof?
The same spirit as what I said about the early universe.
Okay, so thank you.
It is multiverse is an easy thing to say, but you can say it. I mean, I will never know. Multiverse by definition is a universe that is disconnected on a different track, so it's very difficult to imagine situation. People have been. I mean, I've seen some papers where people have thought about this universe crashing into the other universe, hence some signal. I mean, why would it do that is my first question. I mean, I don't even see exactly a lot of possibilities. Multiverse, the first time these were talked about were probably in the context of interpretation of quantum mechanics, like multiple copies of it. It is to invoke something called anthropic principle. We happen to be alive because our universe had the right values of everything. This again depends on people, scientist to scientist, again it's in that realm. I mean, I personally think that's the most saddest thing that can happen where we say, oh, it happened because it happened to be so. Right? I mean, that's not how we do science. Or particularly in physics, I mean, definitely we don't do that.
Yes, sir, thank you.
So around us, we can see the universe up to 43 billion light years away. Okay, now you know what a light year is? Light year is the distance that light travels in 1 year. Okay, now that's enormous. Let me not try to, I don't know how to put it in easiest case. No, but then 43 billion is 1,000 million. Million is 1,000. 43 light years. Okay, so but it's a huge part of the universe you can see. But it's interesting that beyond that we can't see in light. Okay, so we have to depend on other ways to go beyond that. Absolutely, this is a fantastic question. I mean, it would be very amazing if there aren't any other intelligent systems, because in the very nearby, so we are talking about light years, right? 30 light years away, or 300 light years away from us, we have seen already few thousands of planets. I mean, planets around other stars. Okay? We haven't found an Earth-like planet, but we know why we will not find it. I mean, it's difficult to imagine that our sun happened to have a planet which happened to give life. Okay? That's one answer. And since we are talking about Professor Narlikar, I should tell you, there is, the question is how does life originate? And one school of thought is the universe has a lot of life, okay? And their life is transported on comets and various bodies coming from various areas, right? We have this extra solar system visitor, so from some other solar system, what was it called? It has a Hawaiian name. Okay, so they may carry, and we also have seen signatures of very complicated molecules in distant bodies. So it's not completely unimaginable that maybe life as we have it is there everywhere. It's like, the way trees disperse seeds. Not every seed goes and grows. But maybe there's a dispersion of seeds and some land in the right planet and then they took off. So that happened on Earth. Possibly. Again, I'm not an expert, so there are actual calculations you can do. Sorry.
Regarding your personal experience with Dr. Narlikar. So we also know him as mathematician, right? Originally, he was an angler, senior angler, right? And so, but he went into cosmology with Dr. Ryan, and then he went in. In your personal experience, how much he was also involved in the mathematics of it, whether through cosmology or out of his strength, how much he was really a mathematician along with the cosmologist, in your personal interactions with him?
There's no question about it. And it's not a surprise. Cosmology comes out of a field called gravitation, and general relativity in India was actually in the maths departments. His father was a very well-known general relativist. So certainly anyone who works in these areas have to be very good in mathematics, have to have a mathematical mind. Okay, now why I said he, in my recollections, was always thought in those mathematical terms. Right? He was also physicist, but he had a maths thing. So you're right, the fact that he was a wrangler was no coincidence. He thought very mathematically. In fact, this action at a distance. So again, I don't know whether it was appropriate for this audience, but I was also preparing a talk which I would give in some skills. And to me, that is what struck me. He believed that, okay, if mathematics is telling you there are two solutions, and you have no real reason to choose between them, he would prefer to work for a solution where both are there, yet some other thing happens, like the universe has some strange properties that allow you to live with that mathematical consistency. To him, mathematical consistency made him. Which is why he was so upset with Big Bang. Because Big Bang does say it will be singular, mathematically. Right? There will be a singularity. So in that sense, yes, I think your reading is right. I just said one thing slightly different was I focused on only working on things that can be observationally verified. As a faculty, I've never worked on anything that cannot be measured. Okay? And just like the discomfort I have with early universe, so I work on things, finding ways to measure things there. Just not see that is happening. Similarly, the multiverse, I have this big problem that you can say there's a multiverse, but there's more. Right? I think physics should be verifiable. Again, there are a lot of debates on this. Okay? But there should be a falsifiability. If you say this happens, and you say there's no way you can tell me whether I'm right or wrong, then that statement to me doesn't fall in the bracket of science, right? If I have to just say, okay, this glider can be anything, but I can't ever, you can never tell. Okay, so you can never tell is not part of science according to me. But I can also tell you there are enough people who would argue on the other side. And I am not, as I said, neither am a science historian, I also don't like such debates. I don't involve myself in this thing.
Thank you, sir.
Sir, I have a doubt.
Oh, okay.
So some scientists are telling that the sun will run out of hydrogen and helium in a few billion years, and like life on Earth may not exist. What are your opinions on it?
Yeah, that's a fact. The fact that sun will end its life in 2 billion years is something that we know extremely well. We are seeing stars die. As we have better observations, people see this happen that, according to me, if you are near sun or near a black hole, yes, your clock will appear to slow down. Okay, but you as a person sitting with the clock, you will see no difference. Okay, do you like this going as have you seen this movie? Interstellar? Yes. So that has, it's a very learning movie. It has concepts which are not really, but it tells you about this person who goes to the black hole, coming back, the other guy has aged by decades. This still happens. This again to know happens because we see it on small scales happening with many systems. So there's no opinion on it. It's a observed fact. But it is interesting. So that's what I'm saying. The last 100 years, the 130 years of physics have been quite mind-boggling. So we used to always think that we do science, everything happens in some given space and time, as there is a clock that runs the same everywhere. Actually asked me, so there a gravitation field every day, what it does. Even without that, we also know that if you are moving at very high speed, your clock versus someone else's clock is different. Relative velocity of the two, the clocks. So these are facts that we are coming to terms with. So we used to think of free space. At that time, we had no problem saying that this direction can mix with each other, because I can stay complicated. Now, it's just that time also can mix in space. Right? So there is another dimension which we know has mix. You can rotate from one to the other. Right? I can make the x-y axis change, right? I can make the x-axis go to the y-axis. So now imagine you are able to do with time and x. We are able to do that. Not only we are able to do that, we know that nature does it. So nature is such that it happens to us. And it is the fourth. There are people who also think there are many more different dimensions, language differences. But those are again in that orange band that I showed you. The sun goes around the galaxy, right? So it's a simple vector equation, right? It's like the Earth going around the sun. Like you imagine the solar system going around there. You can compute what its velocity should be by counting up the stars which are between us and the center of the galaxy. You will find that the sun is moving at a much faster speed. Consider it. It should be, 140, 120 kilometers per second. It's moving at 40. Which means there's matter there which we are not able to see. That's at galaxy as we see that. Then at clusters of galaxies, we see a lot of, reasons the galaxies are moving much faster than Now this is again interesting. So, and then at the cosmological scale, I told you about this cosmological background. So we measured it extremely well. That's one of the very well measured things. It's best explained, and it's difficult to explain what you see without evoking dark matter. And dark matter and ordinary matter, the thing is they don't interact with each other. That's very important for explaining what we see. So these are all evidence that there is something like that. So we are very confident there's something like that, but we don't know what it is.
There is time travel possibility.
Time travel. But again, I mean, mathematically there's nothing. I do is looking at what is called the last phase structure of space and time, given the last phase distribution of matter and radiation. This is the possible guide. But every element of that, there's a person who spent their entire life doing it. So for example, for me, galaxies are like dots. Right? I showed you this expanding dot. People spend all their lives understanding how a galaxy is very different structures. 100 billion stars. Right? They are born, they die, they spread out radiation, all kinds of things. That's also cosmology because that is how stars form, how the first objects form. So there are various aspects of cosmology. In simplest term, I can tell you what is attractive about cosmology. Okay, it's like a field which is quite like a creative, where you need every type of physics that you need. I can be a cosmologist based on my understanding of very quantities, things like that. I can be a cosmologist who just knows how to do gas relations, more like an engineer. There are many areas in cosmology. That is what is exciting. I find exciting about it. Any problem has aspects from very different sciences. Someone asked about time. That's a cosmology problem. You should be able to compute a lot of things. And the final discovery was how rare is time, how difficult is it for light to coordinate. We don't know, right? That factor, unless we know, we can't tell you whether how probable that is. So, it's hard to work.
Sir, what do you think of white
Jayant worked on white holes, one of his students, who is now one of the very famous because of gravitational waves, had his PhD thesis on white holes. White holes are again possible. The gentleman asked me about Narlikar's mathematical things. Anything that was mathematically possible, he took it very seriously. White holes are mathematically possible. But physically odd. And we haven't seen any examples. But we see jets coming out of that.
So that in this program, our request our director, Dr. Guru Prasad, to hand over and explain what is happening from our side.
Oh.
I also take this opportunity to give myself.
It was a great moment here today, listening to the contribution of Narlikar to science and society, which made us even prouder. Professor Narlikar was indeed a legend, not only for modern Indian astronomy, but also as a popular science communicator. And as a popular science communicator and an institution builder, it was a great privilege to listen about the legendary cosmologist from an eminent cosmologist who is none other than Professor Tarun. Sir, it was a great to listen to you and thank you for sharing invaluable information about Professor Narlikar. I also thank distinguished scholars from many research institutes for your august presence in this lecture event. I also thank the science enthusiasts, particularly the kids from various schools here, for their active participation every time we organize such events. I would like to thank the media for covering this event. Also, I thank all our staff members of JNP for their involvement in making this event a